So, have you ever wondered what happens when an ancient spiritual journey smacks right into the cutting edge of theoretical physics? Well, today we're diving deep into that. We're going to explore how some of the most advanced science out there is actually giving us a whole new language to think about one of the most profound events in Islamic tradition, the Isra Miraj. Let's see how these two seemingly different worlds might connect.
At its very heart, the Isra Miraj is described as a journey that just shatters the rules of our everyday reality. It's not just about traveling really, really fast. It's about stepping completely outside the fabric of space and time as we understand it. This is an event that, just by its nature, challenges our most basic assumptions about how the universe works.
And that leads us to the big question, right? This isn't about science trying to prove a spiritual event. Not at all. The real question is, can the incredibly strange and fascinating rules of modern physics give us a new framework, a new set of tools to even begin a conversation about something so far beyond our normal experience?
Okay, so first things first, we have to get our heads around the core concept. This isn't just a story about something that happened in the past. It's about a phenomenon that exists in a state that researchers, like Sabella and their colleagues, actually describe as being time-free. Think about that for a second. Imagine something happening not within the river of time, but completely outside of it. This isn't a story about getting from point A to point B in a certain amount of time. No, it's about transcending those ideas entirely. It's a place where the rules of before and after, they just don't apply. Now, to even start to wrap our minds around that, we first have to realize that our everyday gut-feeling understanding of space and time, it's been totally overturned by science in the last 100 years or so. What we think of as normal is, well, it's anything but.
For centuries, we had this classical Newtonian view. It was simple. Space was a big fixed box, and time was this universal clock that ticked the same for everyone, everywhere. But modern physics came along and just smashed that idea to pieces. We now know time can stretch and shrink depending on how fast you're moving and how strong gravity is. And space? It's a dynamic, bendy fabric that's woven together with time. And the conversation is far from over. I mean, this is a living, breathing field of science. You've got researchers like May who are actively questioning even the core ideas of relativity, pushing for new models to explain the universe's biggest mysteries. The key thing to remember is that our understanding is always evolving.
One of these wild new directions is the theory of space quantization. Okay, so think of reality not as a smooth, continuous movie, but more like the screen you're watching this on. It's made of tiny, individual pixels, or quanta. If space-time itself is built from these little indivisible blocks, then maybe, just maybe, the rules for moving through time and space can be bent, or even broken at that super fundamental level.
And that brings us to some even more out there, but really powerful ideas. If space-time isn't this smooth thing we thought it was, then what could it be? This is where we get into the truly mind-bending world of quantum gravity. All right, stick with me here, because this one's a trip. The holographic principle suggests that our entire three-dimensional reality, you, me, the planet, the galaxy, might just be a projection, like a hologram. And all the information that makes up our 3D world is actually stored on a flat, 2D surface at the edge of the universe. If that's true, then maybe travel isn't about moving through space, but about accessing the information, the underlying code of reality itself. And here's where we bring it back. A researcher named Chisti uses concepts just like this to talk about events like the Isra Miraj. He frames them not as physical travel, but as quantum gravitational manifestations. Now, that's a super technical way of saying it's an event that operates on the deepest, most fundamental level of reality's code, a level where our normal rules of cause and effect, and even time itself, might not even exist.
So you see what's happening, right? We've got all these different researchers from different angles, all circling the same incredible idea. Whether you call time transcendent, or something that only emerges when we measure it, like Sorley suggests, or something with its own quantum weirdness, the takeaway is the same. Time is absolutely not the simple, straight arrow we think it is.
And look, this isn't just a bunch of thought experiments on a chalkboard. Scientists are building ridiculously sophisticated tools to actually visualize and simulate these crazy concepts of space-time. They're literally developing ways to model what seems impossible.
So you can think of these diagrams as like next-level maps. Instead of just showing north, south, east, and west, they help physicists actually see the complex ways space-time can twist and warp. They're tools developed by people like Harish to turn the abstract math of relativity into something we can almost picture.
But for the really, really extreme stuff, like the moment the universe was born, or what happens inside a black hole, or even a hypothetical event that happens outside of time, diagrams just aren't going to cut it. That's when scientists have to bring out the big guns, supercomputers, and a method called numerical relativity.
So how in the world does this work? Well, it's pretty wild. First, scientists feed the computer a set of initial conditions for a chunk of spacetime. Then, they let these massive supercomputers run simulations, letting that spacetime evolve according to the laws of physics. This lets them analyze what happens during insane events like cosmic bounces, and finally, they can create visualizations of how space-time behaves in these totally bizarre situations, stuff you could never solve with just a pen and paper.
Okay, so let's put all the pieces on the table. On one side, we have this transcendent spiritual event. On the other, we have the absolute frontier of theoretical physics. So where do they meet?
And this right here is the most important takeaway. The whole point of looking at quantum physics or holographic principles isn't to prove the Isra Mirage. No, it's that this new physics creates a conceptual space, a sort of intellectual playground, where an event that claims to transcend time isn't automatically impossible. It gives us a language to even begin to talk about it.
At the end of the day, it all comes back to time. The old idea of a universal clock that just ticks away for everyone is gone. We're moving toward a view, synthesized from the work of researchers like Sorley, where time is contextual, it's relational, it depends on who's looking. And in a universe where time itself is that slippery, the definition of what's possible gets a whole lot wider.
So I want to leave you with this final thought. The deeper that physics digs into the nature of reality, the stranger and more counterintuitive our universe becomes. We're finding out that space-time can be pixelated, it can be a projection, it can be simulated in ways we never, ever dreamed of. So as that line between what we thought was science fiction and what is actually science fact keeps getting blurrier, where do we even begin to draw the line between what's possible and what we call a miracle?